Alright, so for our first formula, we're going to be looking at PBr5, and we know that P and Br are both nonmetals, so therefore we have to have a molecular compound here. And P is phosphorus, and when we're naming molecular compounds, we do not put prefixes for the very first element in the compound if there's only one, so it's just going to be phosphorus. And we've got 5 BRs, so that's going to be 5 bromines, and we're going to put that into naming it. We're going to use the prefix penta for the 5, and we're going to use bromide for the bromines. So we're going to get phosphorus pentabromide. Alright, and for the next one, we have N2O. Again, we have 2 nonmetals, so we're going to have a molecular compound. We have 2 nitrogens here, so we're going to want to use the prefix di for the nitrogen. So we're going to get dinitrogen, and we've got 1 oxygen, so we're going to use mono for the oxygen, and then we're going to change it to ide for naming it. So we're going to get dinitrogen monoxide. The next one here is pretty tricky. You've got a transition metal and a polyatomic ion, and because it's a metal and an ion, a polyatomic ion, sorry, you're going to have an ionic compound. And then the charges here are tricky because of the transition metal. You can't just use the regular crossing rule. You have to actually go and look at the charges themselves, because sulfate has a -2 charge, which means that when you crossed it over, there was a canceling out and you got TiSO4 too. So there is actually, the charge on your titanium will actually be 4, and you will see that in the name when you get titanium 4 sulfate. Because it's an ionic compound, you don't use any prefixes, and because it's a transition metal, you're going to use the Roman numerals to represent your charge on your metal. Alright, the next one is a metal and a nonmetal, giving you an ionic compound. It's fairly easy to name. It's just magnesium and oxygen, and you're going to change that oxygen to oxide, so you're going to get magnesium oxide. We have another transition metal and polyatomic ion here, so you're going to have an ionic compound, and your hydroxide has a charge of -1, and here you can actually use the cross backup charge rule, and you're going to see that your copper has the charge of 2, so you're going to get copper 2 hydroxide. Alright, moving on to the next one, we have 2 nonmetals again, so you're going to have a molecular compound, and you've got 1 singular sulfur, but it's the first one, so you're not going to use mono there, so you're just going to have sulfur. And then you've got 3 oxygens, so you're going to get trioxide, so sulfur trioxide. Here we have a metal and a nonmetal, giving us an ionic compound, calcium and oxygen, so you're going to get calcium oxide. Again, metal, nonmetal, ionic compound, and you've got iron, which is a transition metal, so you're going to figure that charge out, and you see that oxygen's charge is -2, so you can use the cross-up charge rule again, and you're going to get that iron's charge is going to be +3, so you're going to get iron 3 oxide. And we've got a metal and a polyatomic ion here, so we're going to have an ionic compound, and we're going to have, this is a regular metal, so you don't have to do any charges, and Mg's charge is +2, and so is sulfate, so that's why those charges are canceled out, and you're just going to get magnesium sulfate. Alright, now we're going to be looking at names and getting the deciding if it's ionic or molecular, and then getting the formula. So we have calcium chloride here, so that's a metal and a nonmetal, so it's ionic. And our formula will be CaCl, And then we gotta check our charges, and the charge on Ca is +2, and the charge on Cl is -1, so you're gonna get CaCl2 when you cross your charges. Alright, potassium carbonate, that is a metal and a polyatomic ion, so that's an ionic compound. And you've got your charge on K is +1, and your charge on carbonate, CO3, is -2. So you're going to get K2CO3 for your formula. Iron trichloride, you can actually see, kind of note by the prefix, that it is going to be molecular here, because you can see in molecular formulas, compounds, in the names, that's when you're only getting the prefixes. But you also know that iodine and chlorine are both nonmetals, so you're going to get a molecular compound. And when you're creating the formula, you've got a singular, you just see iodine, so you know that's just going to be 1, and you've got trichloride, so you know you're going to have 3 chlorines. And it's the same situation for the next one, molecular, and you've got 1 sulfur and 4 chlorines, so you're going to get SCl4. For manganese 2-phosphate, you know that manganese is a transition metal, so it's ionic. Manganese is a transition metal, and phosphate is a polyatomic ion, so that's why it's going to be ionic. And you already have manganese's charge, and you know that phosphate's charge on your reference sheet is -3. So with the +2 and the -3, you're going to cross charges and get Mn3 PO4 2. Next we have tin, another transition metal, and fluoride. So that's a metal and a non-metal. So you're going to get an ionic compound. And you know tin's charge here is 2, and fluorine's charge is -1. So when you cross charges, you're just going to get SnF2. For ammonium hydroxide, you have the only positive polyatomic ion with another polyatomic ion hydroxide, and so it's going to give you an ionic compound. You know that NH4 is +1 on your reference sheet, and OH is also -1 on your reference sheet. So those are you could cross charges, and they're just going to give you NH4OH. Next, we have another prefix, and then also 2 nonmetals. So you're going to know that it's molecular. And dihydrogen means you're going to have 2 hydrogens and 1 oxygen in that order. So you're going to get H2O for dihydrogen monoxide. And then for xenon hexafluoride, you know that xenon and fluorine are both nonmetals. So again, that's a molecular compound. And you're going to get XeF6 because of the prefixes. Alright, so we're going to be determining the mass. Percentage by mass of nitrogen and ammonium sulfide, NH4 2S. So the easiest way to do this is you're going to identify how many of each element you have in your compound. So we've got 2 nitrogens, 8 hydrogens, and 1 sulfur. Alright, so you're going to determine the mass of each element individually. So you've got 2 nitrogens, so that means you've got 2 times 14.01, so you're going to have 28.02 grams of nitrogen in this. And then for hydrogen, you're going to have 8.08 grams, and for sulfur, you're going to have 32.07 grams. This is all going to add to give you 68.17 grams total of the whole compound. So when you're finding the percentage by mass of nitrogen, you're going to take the mass of the part, which here is nitrogen, divided by the mass of the whole, and then you're going to multiply it by 100 to get your percentage, and you're going to have 41.1% mass of nitrogen in ammonium sulfide. Alright, so when we're looking at the empirical formula for C8H8O4, we know that empirical formulas are just the lowest possible formula for your molecular formula. So we see here that the lowest number is oxygens, which is 4. So if we take out that 4, we can take a 4 out of each of the 8s for C8 and H8. So you're just going to get C2H2O. Alright, so the empirical formula of a compound is NO3, and its molecular mass is 186.00 grams per mole. What is its molecular formula? So we're going to use this formula it's the mass of your molecular divided by the mass of your empirical formulas will give you the factor that you need to get your empirical formula to your molecular formula. So the first thing we got to do is find the mass of our empirical formula, which we want to start by looking at how many of each element we have in our compound. So for NO3 we have 1 nitrogen and 3 oxygens. So we're going to do 1 times 14.01 for nitrogen and 3 times 16.00 for oxygen. We're going to get a mass of 62.01. Alright, and we're just going to do 186.00 and divide that by 62.01, and we're going to get 3. And so that's our factor now. So now we're going to do nitrogen, which is 1, and multiply that by 3. So we're going to get N3, and then O, which is 3, multiply that by 3, which is 9. So we're going to get our molecular formula is N3O9. So here we're going to be determining the empirical formula from the percent composition. So that's percent to mass, mass to mole, divide by small, and multiply to a whole. So the first thing you're going to want to do is take your percentages and turn them into masses. So here we are. So we're just going to assume that our compound in total has 100 grams. So with carbon having 64.9 grams, hydrogen having 13.6 grams, and oxygen having 21.6 grams. So we've got our percent to mass. Now we're going to change our masses to moles. So here are our, in dimensional analysis, our factors. So there's 12.01 grams in 1 mole of carbon, and 1.01 grams in 1 mole of hydrogen, and 16.00 grams in 1 mole of oxygen. So now we're going to figure out the moles. So when you work out that math, you're going to get 5.40 moles of carbon, 13.47 moles of hydrogen, and 1.35 moles of oxygen. And here we're going to divide by our small, which is 1.35. And we're going to get 4 for carbon, 9.97, which can be rounded to 10 because it is within 1/10 of a place. And then oxygen is going to have 1.0. And so now we're just going to plug all those back into a formula, and we're going to get C4H10O. Alright, so here we're going to be determining the molecular formula of the compound. In the previous question, if its molecular mass is 148.0 grams per mole. So just bring back that formula of the mass of your molecular formula over the mass of your empirical formula is going to get your factor. But so we have the mass of our molecular formula, but not our empirical formula again. So we just got to figure that out. So in our empirical formula, which is C4H10O, we know we're going to have 4 carbons, 10 hydrogens, and 1 oxygen. So we're going to figure out this mass of the empirical formula, and we're going to get 74.14. And when we divide 148 by 74.14, we're going to get a factor of 2. So we're just going to multiply all of our subscripts here by 2. We're going to get C8H20O.